Bismillah ar-Rahman ar-Rahim. Now we are going to practice some examples just to show you how problem solving techniques related to the concepts of magnetic field due to a straight long wire. So this example here says that two long wires, see the word long here is important, they're actually very long wires, are oriented so that they are perpendicular to each other. So this wire here is in this plane, and this wire is coming out. See, they are perpendicular to this plane here. So they are perpendicular to each other, as shown in this figure here. And you can see that the current in this wire is in this direction here, and I'm calling it IB. B means bottom, is 5 ampere to the right, and this current here is coming out of the board. IT top, you see the top wire, is 20 ampere, and the current, since there is a dot, it means it's coming out. This is a cross section, okay, and this is a side view. So this wire is coming out, and this wire is to the is parallel to this plane, to the board. He wants the magnetic field due to these wires at the midpoint between them. Okay, that's the idea. So find the magnetic field B, the net magnetic field. So there is as you know, when you pass a current through a wire, you produce a magnetic field. And I hope you remember that if you have a wire like this with the current I, the magnetic field actually will be like this. Okay. Okay. So it rotates at a distance r, perpendicular distance between so the magnetic field rotates. Okay. So if you have your wire like this, the magnetic field will be doing something like this. Okay. Rotates. Okay. Rotates. And it's given that magnetic field B is given by mu 0 I, the current, over 2 pi A or R. Okay. Let me call it A here. A is the distance between the wire and the point P. If the current is like this, the magnetic field will rotate in this direction. Okay. Okay. And if the current is down, the magnetic field will be in this direction. Okay. Down, current down, thumb with the current, the fingers are with the magnetic field, and it rotates around the wire. Okay, let's now apply this rule here to these two wires. Since we have two wires, which means we have two magnetic fields at this point, and since we have, let's look at the wire in the top. Okay, the top wire. The top wire has a current I top equal 20 ampere. Okay, I want to know the magnetic field at this point. This point here, midway. This is 10 centimeters. The distance between the wire and the point is 10 centimeters. That's the distance A here. Huh? That's the distance A. And can you tell me what is the direction of the magnetic field at that point? Direction of the magnetic field due to this current. You see, you put your thumb with the current, and the magnetic field rotates. So at this point, the magnetic field will be down. At this point, it will be to the right. Magnetic field here will be to the right. I call it B top. Okay, that's the direction of it. And the magnitude will be by this formula here. Okay. At this point here, the magnetic field will be going up. At this point, it will go to the left. At this point here, it will be go to the down like this, and it rotates in a circle. Okay, that's the circle I'm talking about. Okay, it rotates, and it's always perpendicular to perpendicular here. Okay, between the point and the magnetic field and this distance here. It's always perpendicular. So here, you see the perpendicular here, 90 degrees between R or A and the vector B. That's the magnetic field due to that wire. Let me go to the wire which is in the bottom. I'm going to make it in blue like this. That's the wire. It's a very long wire, and the current I bottom is in this direction. Can you tell me what is the magnetic field? So you put your thumb with the current, and the magnetic field will rotate. Okay, it will rotate. At this point, the magnetic field due to that wire, the wire in the bottom, will be out. Will be coming out of the board. Okay, it will be coming out of the board. Okay, let me draw it here like this. B bottom. Okay, B bottom. It will be coming out. Okay? At this point, it will be going down. Here, it will be on this side, it will be going in. Okay? And so on. So that it rotates. You see, it rotates around the wire itself. So I have two magnetic fields, one in the bottom, and the distance here, of course, is 10 centimeters, the distance here. Because this point is a midway between the two wires. 10 centimeters. 10 and 10, the distance between the two wires is 20 centimeters. But I'm interested in this distance here. That's the A, which goes in the formula here. Okay. So now I have two magnetic fields. One which is in this direction, and one coming out, and they are perpendicular. The two magnetic field. The two magnetic field I'm talking about, they are perpendicular to each other. And so I'm going to first of all write B top. It will be mu 0 I top over 2 pi A. And that's mu 0 is 4 pi and to the power minus 7. The current in the top is 20 ampere divided by 2 pi, and the distance is 0.1 meter. That's the distance between the two wires, okay? Between the wire, and the point where you want to find the magnetic field. And that magnetic field will be 5. If you do correctly the calculations, it will be 4 10 to the power minus 5 Tesla. 4 10 to the power minus 5 Tesla. That's the magnitude of this magnetic field, and its direction is here, okay? Now we go to B bottom. We use the same formula, okay? I bottom. The only difference here will be the current, because A is the same. So 4 pi and to the power minus 7. Of course, here the pi will cancel, the 2 will cancel, then we have a 2 here, okay? Same thing here. And the current here will be, we have to use the current in the bottom, which is 5 ampere, okay? Divide 2 pi, the distance between the wire and the point, okay? 10 centimeters and 10 centimeters. 0.1 and 0.1, the same. So if you do the calculation correctly, you should get 1 and to the power minus 5 Tesla. That's the magnitude of these two magnetic fields. Now remember that these two magnetic fields are perpendicular to each other. So if I want to find the magnitude of the net magnetic field, okay, B net will be the magnitude of that magnetic field will be the square root, just the square root Pythagoras, okay? B top squared plus B bottom squared. Okay? That's how you do it, okay? Because they are perpendicular, okay? So if you have two vectors which are perpendicular to each other, this is B top and B bottom. These are not. It's not correct here. I'm just showing you how to get the resultant. Okay, the net. This is B. This is B. Okay. This is B net. Okay. That's B net. How do you find B net from this figure here? You square this plus square this and take the square root. Okay. By the way, the B top and bottom are not the same here. I'm just showing you how to, because these two are perpendicular, I can use this formula here to find the magnitude of the net magnetic field. So you put the numbers there, square root of what? 4 10 to the power minus 5 squared plus 1 10 to the power minus 5 squared, square root of that, and you should get 4.12 10 to the power minus 5 Tesla. That's the net magnetic field, the magnitude of the net magnetic field at this point here. Okay? So remember, we are using this formula here because we are talking about long wires. Okay? Long wires. When you have long wires or very long wires, you can use this formula for the magnetic field. And that's the final answer here. That's the net magnetic field. Okay? At this point here, which is made of the we have two magnetic fields here, one due to the bottom, the other one top, and you take the square root of the squares, you get the net magnetic field. Magnitude of the net magnetic field. He didn't ask about, he did not ask, you see here, what is the magnitude of the net magnetic field. He did not ask about the direction. Of course, the direction will be, since this is coming out, the net will be in this direction somehow, in this direction like this, okay? Okay? It will be pointing in this direction. And this is its magnitude, okay? Thank you. Okay, this is another example related to magnetic field due to a straight long wire. This time we have also two wires, but you see the configuration is different from the previous example. The two wires are parallel, as you can see them here. Okay, this has a current in this direction, I1, and I2 is unknown magnitude and direction. Okay, it says two infinitely long. Sometimes they say long, sometimes they say very long, sometimes they say infinitely long. All that because we want to use the formula, which is mu0 I over 2 pi a. Okay, so they are carrying current wires are parallel to each other, as you can see them as shown in the figure. The net magnetic field at point P, which is midway between them, this is midway, which means this is 1.5 centimeters, 1.5 centimeters. Okay, the whole distance is 3 centimeters. The magnetic field midway between them is 0.12 millitesla and out of the page. So the net magnetic field is out of the page. Okay. The current I1 here is 12 ampere. What is the magnitude and direction of I2? Of course, I2 can be going either to the right or to the left. It cannot go otherwise. Okay, either to the right or to the this current is going to the right. Okay, so so B net at point P is 0.12 millitesla. Milli then minus 3 Tesla. Okay, and B. So B. Let's calculate B1. B1 is the magnetic field due to the current I1. What is its direction, first of all? Okay, I'm going to use my hand. Okay, the current, my thumb with the current, the magnetic field here will be in. It rotates on this side, it will be out. Okay, so here it is in, and let's calculate its magnitude. Okay, I'm going to use a formula for the long wires, mu0 I 1 over 2 pi a. What is a here? Is the perpendicular distance between the wire and the point. Okay, that's the distance here, and we know that the current, the magnetic field is inside for this for B1. Okay, so 4 pi to the power minus 7 times the current I1, which is 12 ampere, it's given to you, divide by 2 pi. The distance it is 3 centimeters, 0.015 meter. Okay, that's the distance in meter. So the pi will cancel, the 2 here will cancel, you have a 2 here, and if you do the calculation correctly, you should get 1.2 10 to the power minus 1.6 10 to the power minus 5, 1.6 10 to the power minus 3 Tesla. 1.6 minus 4, sorry, minus 4 Tesla. Okay, minus 4, 1.6 10 to the power minus 4 Tesla, or 0.16 10 to the power minus 3 Tesla. Okay, so let's compare these two numbers here. That's the magnetic field, which is the net magnetic field, and this is only due to B1. As you can see, and this is in, and that magnetic field is inside. It's important to know the direction, and this is outside. So, and this is larger than this. It's outside and it's larger. Okay, so what do you think about, so B at point P, which is smaller than B1, it is smaller than B1, it means it is B2 minus B1. Okay, that's how you this is how you get B at point P, smaller than B1. B1 is inside, so inside will have a minus sign. Okay, as you can see, B1 is inside, it has a minus sign. B2 is outside, it has a plus sign because it says out of the page here, and out of the page. So B at point P, the net magnetic field, that's the net. Okay, is outside. So B2 should be outside. So that when you take B2, which is, I don't know B2 yet, but when I subtract from B1, I get smaller number. You see, you say I get smaller. B net is smaller than B1. It has to be like this. Okay, so this magnetic field has to be outside. Okay, outside, and this is inside. The inside, it's known because I know the current, so it is inside. Okay, so, and this is outside. Okay, so the idea is to write this equation correctly. Okay, B at point P is outside. It says it's out of the page. Okay, when I say outside, that means outside the page. Okay, it's out of the page. B at point P. So from this equation here, I can find that B2 will be B at point P plus B1. I take B1 to the other side. Okay, so B at point P is what? 0.12 and to the power minus 3 plus 0.16 and to power minus 3. That's the magnetic field at point. This is the magnetic field at point B due to B2. Okay, due to a current I2. That's the magnitude of the magnetic field, and it has to be outside. Okay, it has to be outside. And this is 0.28 and to power minus 3 Tesla. That's the magnitude, and its direction, since it is positive, its direction should be outside. Okay, it's outside. So already we know the current here to have a magnetic field outside due to the current I2. I2 should be to the right. So the current I2, I can write here the current I2 is to the right. Okay, it has to be to the right to make B2 outside. Okay, to make B2 outside. So we said that B2 has to be outside, so that when I subtract from B1, I get a smaller value for B net. B net is smaller than B1. You can see it. Okay, it's smaller than B1. And this is how you write. This is important equation to write. Okay, if you don't write this correctly, you will never be able to solve the problem correctly. Okay. So this is so now let's calculate the current I2 since we have B2. Okay. Now let's now calculate the current I2. So I write B2 is mu 0 I over 2 pi what? 2 pi A. A is the distance between the wire, the perpendicular distance between the wire and the point. Okay. So I'm looking for I2 here. Okay. Let me write down I2 here. Huh? I1 is there and I2 is here. And this value B2 is given to you. You found it already. So, and this should be equal to 4 pi and to power minus 7. I2 is unknown, divided by 2 pi A. A is 0.015 meters, okay? 1.5 centimeters. So the 2 will cancel, this here will cancel, and this should be equal to 0.28 and to power minus 3. That's the value of B2 that we have found. Remember, huh? Now, if you do the calculation correctly, you should get I2 21 ampere. So that's the magnitude of that's the current. Okay, that's the current, and this is its direction is to the right. Okay, the current I2 is to the right. That's the answer to the question here. What is the magnitude and direction of the current I2? Okay, so that's the point. It's very important to understand this point here, my son, because this is not trivial, and it's not trivial to understand this point here. You see, B1 is larger than B net. It means, and it's inside. When inside, I mean I have to put a minus sign here when I write the equation here for the net magnetic field. Inside minus sign. So this is smaller than this value here. It means this number is large. So a large number minus small. This equation has to hold. Okay. So from where you can find B2. Okay. That's the value of B2. That's the magnitude of B2. And B2, the magnitude of B2 is this, and its direction should be outside, should be out, okay, to be able to solve the problem correctly. And that's the current. It is to the right. Thank you. This is the last example related to magnetic field due to straight long wires, and this is a conceptual question. There are no calculations here, okay. And conceptual questions are very important because you see some of them in exams in your textbook, and you are supposed to be able to solve them. So the we have four configurations here of wires, long wires. Okay, 4 different set of wires, and these wires are infinitely long, and you can use this formula here to find the magnetic field magnitude. They cross each other without touching. You see those wires here? Let me show you here. These are 4 wires. You can see them here. Okay. They form a square, okay, and the current is the same in all 4 configurations, but the direction of the current is different. You can see them. Okay, the direction of the current in the wires from one configuration to another, they are different. Okay, it says for which configuration will the magnetic field at the center of the square found by the wire equal to 0? He wants the magnetic field to be 0 in the center here. In which configuration? Only one of them has a magnetic field equal to 0. So let me show you now quickly here on the side. Give you an example of a square. Let's take the first configuration here. Of course, here the current here is I like this, and the current here is like this, and the current here on the right is in this direction, and the current here is to the right like this. Okay, that's the current, the direction of the current in the 4 wires in configuration number 1. Okay. Now let's go to in the center. In the center, it means I am here. Okay, that's the center of your square. Okay, I have 4 magnetic fields. Each wire will produce a magnetic field in the center. You can see mu 0 I over 2 pi a is the same for all of them. This distance, and here are all the same, and the current are the same. So B is the same for each wire. For this wire and this wire and this wire and this wire, for the B is the same. Now let's look at the directions now. For the top wire, the magnetic field is inside. So here I'm going to write inside. It's only its direction. Okay. If you go to the right wire, this is the right wire. The magnetic field at this point is outside. Okay. So I'm going to write here outside. Okay. Outside. Okay. Now in the bottom wire, the magnetic field, the current is in this, so it's outside also. Okay, the magnetic field is also outside. In the top wire, in the left wire, and the last one, the magnetic field, you can see from here is inside, but on this side it is outside. Okay, so it is outside here. Remember, these magnetic fields are the same in magnitude. As you can see, this inside cancel this outside, but you have 2 outsides. Okay, so the net is not 0. Okay, so these 2 will add up. Okay, so not 0. Okay, we have here not 0. So this is not the case. It's looking for the one which has 0 magnetic field in the center. So this cannot be. Okay, okay, clear. Now let's go to configuration number 2. In number 2, let's do it here directly now, since you already got the idea. Let's look at the top wire. The top wire, the magnetic field is inside. Okay, inside. The right wire, the magnetic field is, it rotates outside. Outside. Okay, outside. The bottom wire, magnetic field is inside. You can see it inside. And its magnitude is given there. This is the magnitude of the magnetic field. It's all they are all equal, these magnetic fields. Okay, and the left wire is inside. Okay, inside. As you can see, these 2 will cancel, and the net will be inside. Here the net was outside. The net, you can add these 2 because they are both of them inside. This is inside and outside. They cancel each other. They are equal in magnitude. They cancel each other. But these 2 will not cancel because they are all in the same direction. So the magnetic field will not be 0 also here. Not 0. So this is not the case we are looking for. Okay. Let's go to configuration number 3. Number 3. Okay. Number 3. The top wire, the current is in this direction. The magnetic field will be inside here for the top wire. It's inside. Okay. You notice that they are all inside because this current does not change its direction here. So all of them, they are inside. You can see them inside. Let's go to the right wire. The current is in this direction, so the magnetic field will be outside. You can see it outside in all of them. Outside. Okay. Now let's go to the bottom wire. The bottom wire is to the current is to the right, so it will be also what? Will be outside. Okay, outside here. Outside. And let's go to the left wire. The current is what? Is inside. You can see the magnetic field is inside. The current is to the up, and is moving up, so the magnetic field will be inside. Okay, this is inside. You notice here that this inside and this outside cancel each other because they have the same magnitude and opposite direction, and this outside and the inside cancel each other because they are in the same magnitude and opposite direction. So here the magnetic field the net magnetic field will be 0, and this is the case we are looking for. Okay, this is this. So configuration number 3 is the correct one. Let's look at the why number 4 is not. You can see here the magnetic field due to the top wire will be outside. You can see it's outside direction. Okay, outside. The right wire is also outside. Okay, outside also direction. Magnitude is given here, and they are all the same. The bottom wire is what? The bottom wire is inside. You can see the current is in this direction, so it's inside. Okay, and the left wire is outside. You can see the current is in, down. The magnetic field from this side will be in, and from this side in the center will be out. Okay, so outside. You can see here that this inside and outside cancel each other, but these two, they will not cancel, and it will be not zero. Okay, not zero. And actually, its direction will be outside because it is. You can see both of them are outside. So here the net will be outside. Here the net will be inside. Here the net will be outside, and here the net will be zero. This is a very important conceptual problem that I hope you can now solve it yourself. Just stop the video, look at the figure, and try to solve it yourself, and try to reproduce this table here. Thank you.